Hey guys, welcome to part 2 of our bonding learning video. I will discuss in this video about bonding pad, capillary design, and bond quality. If you have not watched part 1 video yet, I recommend to do so as well. This is Lito Galera and let's start learning. This slide shows bond pad information for diodes and transistors. The top left photo is a die image of a diode. Diodes only have two terminals. The die back side is a negative terminal or the cathode, while the top side is a bond pad and is also the anode terminal. The bond pad size for this device is 85 by 85 microns and is composed of 100% aluminum metal. The top right image is a MOSFET die which has two bond pads, which are the gate and source. Bond pad metallization is aluminum with 1% silicon and dimensions are over 100 microns. The two bottom images are bipolar junction transistors or BJT. The top side has two bond pads which are the base and emitter. Similar to MOSFET, bond pads are approximately 100 microns or larger and composed of aluminum with 1% silicon and is 2 micron thick. Integrated circuit or IC is composed of hundreds or thousands of transistors and has many more input and output terminals. Each terminal corresponds to a bond pad. The more complex the IC, the more bond pads it has. ICs have similar bond pad compositions to diodes and transistors. But aside from bond pad metallization, there are two dimensions that should be known for ICs: the bond pad opening or BPO and the bond pad pitch or BPP. These two dimensions are critical for determining capillary design. The illustration on the right is an example of IC vertical structure or layers. Notice that the top metallization is covered by a passivation layer except the bond pad opening. Overall, bond pad compositions or metallization is 100% aluminum, with some devices having 1% silicon impurity or even an additional 0.5% copper impurity. Note that these different metallization require different bonding parameters for optimum bonding integrity. Bond pads must also be clean. Must have zero contamination on the surface for bonding to be successful with good integrity. Things to watch out are silicon dust from sawing process, and also occasionally some dies may have passivation layer overextending to the bond pad surface. Other contaminations are organic and ionic contamination. These types of contamination are not visible, therefore is very hard to detect. However, these contaminations can be avoided through proper material handling and storage. And also watch out for oxidized pad, particularly bond pads with copper impurity. One thing that's very common on bond pads is the probe mark. Wafers are typically tested or die sorted, and this is done through probing of each bond pad. Tested or sorted wafers will have a probe mark, and there must be just a single probe mark on each pad. Multiple probe marks means the wafer was retested. Multiple probe marks is not good for bonding as it disturbs bond pad surface and likely will also remove some aluminum metallization. Probe marks must be light, not deep, and should not expose the underlying oxide layer. Let's now talk about the bonding tool or capillary. Choosing the right capillary is very important to set up a stable and reliable wire bonding process. Capillary selection starts with defining correct design or dimension. The illustration on the left is the capillary tip. Critical dimensions of capillary tip that affects first bond are chamfer diameter CD and chamfer angle CA. The illustration in the middle is the first bond, the mash ball pressed by capillary tip. For a good first bond, the mash ball diameter MBD must be within bond pad opening or BPO. A larger MBD will result to a larger contact to the bond pad and likely more intermetallic formation, thus a better bonding strength. But need to make sure that the mash ball is within the BPO. On the right side are sample photos of the gold aluminum intermetallic formation. An intermetallic of more than 60% of the bonded ball contact area is considered a good bond. This slide shows how dimensions CA and CD control the mash ball diameter. On the left side is a capillary tip with CA of 70 degrees. This tip will result to a cone or triangular shaped mash ball. On the right side is a capillary tip with CA of 120 degrees. With larger CA, the mash ball will be flatter and bigger in diameter, resulting to more contact area to the bond pad. CD also affects the mash ball diameter and, more importantly, the contact area where capillary is pressing on the mash ball. A larger CD will result to a bigger mash ball and larger contact to the bond pad, and likely a stronger bond. So what are the correct CA and CD dimensions? The answer to this goes back to understanding your bond pad pitch and bond pad opening. BPP will always be larger than BPO, simply because band pads cannot overlap. A large BPO and BPP will allow a larger CA and CD. A large BPO with smaller BPP may still use the same CA, but CD may be the same or a bit smaller, just to guard bond on bond shorting. For small BPO and BPP, which are called fine pitch devices, a smaller CA and CD is recommended. Since bonding starts with the pre-air ball, how do we know the correct pre-air ball size to achieve the desired mash ball size? We know that the volume of pre-air ball is equal to the volume of mash ball. Mathematically, we can calculate the pre-air ball diameter using the dimensions of capillary, target size of mash ball, and wire diameter. H is the hole size of capillary, along with CA and CD. MBD and MBH are the target size of the mash ball, and WD is the wire diameter to use. The derived formula to calculate the volume of mash ball is equal to the volume of pre-air ball. Most machines allow the users to input the desired pre-air ball size. The calculated pre-air ball diameter would be a good starting point for this purpose. And then you can fine-tune the bonding parameters to achieve the desired mash ball information. We have discussed how capillary design affects the mash ball, which technically is the first bond. Equally important is the proper bonding of the second bond, or what we also call a stitch. A good stitch bond is shown on the image in the left. The stitch has a shape of a fishtail with thickness shaped by the capillary face angle, FA. The next illustration is the capillary tip. Dimension T is the capillary tip size. The stitch length SL can be estimated using capillary dimensions T and CD. SL is half the difference between T and CD. Other capillary dimensions that affects stitch shape are face angle FA and outer radius OR, as shown on the illustrations on the right side. The illustrations are examples only. If you have access to a 2D CAD software, you can draw a capillary tip with target dimensions and then project the shape of the stitch and mash ball. This will give you a better visual of what mash ball and stitch shapes will be. Another thing that should be considered when selecting or defining capillary design is the target loop height. Fine pitch devices have small BPP and will have tight space between wires. It is important that capillary will have enough space to not touch or disturb adjacent wires. In this regard, bottleneck type capillary is required. The illustrations show the relationships between BPP, loop height, and bottleneck height. This slide shows more detailed information about capillary. Capillaries have different material types and finishes, and also different lengths. Knowing capillary information based on part number is something good to have. The information on this slide is from Small Precision Tools, or SPT. You can check their website for more capillary information. Just like any other tool, there is a limit on how long you can use a single capillary, or what's called capillary life. It is common to hear that capillary is worn out when there is a bonding issue. But in reality, capillaries are made of ceramic, which is a very strong material, and definitely do not wear out by pressing a soft gold wire. What actually happens is that there is a gold buildup on capillary tip, and this affects bond quality. In general, capillary lasts for 1,000,000 bonds. Note that one wire is equivalent to 2 bonds because there is a first bond and second bond. Capillary is mounted on the transducer. And when replacing capillary, there are some things that we should take note and do to make sure that transducer and capillary will work as intended. Transducer screw or clamp screw also have its own tool life or limit. A worn-out screw may affect transducer efficiency, so it must be replaced when it reaches life limit. The life limit can be from the equipment vendor or from a study done by the process owner. Just to caution, clamp screw may look like just a regular screw, but its quality is critical. Do not use a cheap screw just to have a cost reduction project. Follow supplier recommendation if there's any, or buy from a reputable company that will provide you consistent material quality. Clamp screw must also be tightened at certain torque specified by supplier. Over or under tightening the screw will result to inconsistent performance of transducer and obviously inconsistent bonding results. Wire bonding is a complex process and involves many parts and parameters that are synchronized and interact at every bond cycle. Everything must be set right for the process to work. It does not need to be perfect, but definitely everything must be within specs. P-parts design and quality is critical to a consistent and stable bonding process. P-parts hold and keep the lead frame or substrate from moving during bonding process. Even a minor movement or bouncing of leads or die-attach pad will lead to a bonding issue, usually a non-stick bond. And for most devices, this is an automatic reject or yield loss. And yield loss translates to a higher manufacturing cost. Correct bond program is also critical. Pattern recognition system or PRS must be taught properly to make sure that machine will find the correct eye points at all times. This is followed by accurately teaching bond location. That is, camera crosshair is properly centered on the bond pad. Likewise, crosshair must also be centered to capillary impression, or what is called capillary offset. These things ensure proper bond placements. Preparation of devices for bonding is important. As we say, garbage in, garbage out. The devices have gone through many process steps. Bond pods and leads may have been contaminated along the way, either from handling exposure to environment, and epoxy outgassing from curing die-attach epoxy. Visible contamination can be detected and screened out through inspection. The bigger enemy is contamination that we cannot see, such as organic contamination. A common method to address this is through plasma cleaning. This cleaning process is performed in a vacuum chamber utilizing oxygen and/or argon gas. Machine variability have significant impact on achieving a stable bonding process. Variability can happen within the same machine, which means inconsistent machine performance. Variability can be between machines of different make. For example, performance of a KNS bonder is different to ASM bonder. Or variation can be between machines of same make and model. For example, KNS bonders of same model have different performance. Likewise, ASM bonders of same model may have same variability. Let's now talk about bond visual quality. Because the bonds or wires are really small, to see the bond quality, the device must be inspected under microscope, usually at 10x to 40x magnification. To see details similar to images on this slide, high magnification microscope is required with magnification of at least 50x to 100x, or even higher depending on the size of the bond. The first image is an example of non-stick on pad, or NSOP defect. This is one of the most common bonding problem. On this defect, there is an impression of pre-air ball impact onto the bond pad, but the first bond did not stick. Usually the mash ball will be present on the lead. If there's no impression on the bond pad, it could likely be the bond pad is passivated or the bond was off target. The second defect is lifted ball. This has similarity on NSOP, except that in this case, the first bond was initially successful, allowing the full bond cycle to complete, including second bond. However, after the bond cycle, the bond lifted up. This is a manifestation of a weak first bond. Several factors may contribute to NSOP and lifted ball problems, such as bond parameters not optimized, worn out capillary, transducer clamp screw, or transducer not being calibrated properly. It is also possible that lead frame or substrate did not sit properly on the pivots, causing vibration during bonding process. Bond pad contamination like silicon dust on bond pad or even deep probe mark and bond pad corrosion is a possibility. Smash ball is another defect, which is simply an overbond. If all bonds have the same manifestation, in most cases this is due to bond parameters are too high. Another possibility could be the bond height is not learned properly. In this case, you will see a smash ball or overbond on random wires. Die tilt caused by improper die-attach process can also lead to the same problem. Indication of this is the problem is only happening on some devices and it is localized within the device. Golf club ball is a defect where the bonded ball actually looks like a golf club. This happens if pre-air ball is not sitting properly on the capillary tip prior to first bond cycle. It could be due to wire tension setup or a kink tail when pre-air ball was formed, or ball is too big. Bond crater is a defect where part of aluminum bond pad or metallization came up with the mash ball, exposing and damaging the oxide layer underneath, which looks like a crater. This defect is typically associated to bond parameters is too high or not optimized. Some devices are more prone to bond crater than others. In this case, it is quite important to optimize bond parameters to address the problem. Oversized ball is simply due to pre-air ball is too big. Reducing the variable size will correct the problem. Overbond stitch is due to bond parameters too high, particularly the bond pores. Reducing the bond pores will likely correct the problem. Optimizing capillary design may also help address the issue. Particularly larger base angle will improve shape of stitch and may allow higher bond parameters without overbonding. Tail-on stitch is an indication that wire after second bond is not breaking properly. This can be due to second bond is too light as shown on the image, which can be due to improper second bond parameters. Also, different lead frame or substrate lead finish will result to different surface hardness and usually requires different second bond parameters. The last image on the bottom right is a weak second bond defect. Visually, it looks weak because of the small and thin fishtail. The weak bond can be confirmed through wire pull tests. Also notice that the capillary impression is light and incomplete. About half of the capillary impression is missing. An incomplete capillary impression is an indication that transducer is not mounted properly. This will also affect first bond quality. To address the stitch shape of a weak second bond, optimizing capillary design will certainly correct the problem. Testing bond strength is very important. Visually, the bond may look good, but this can only be confirmed after bond strength testing. There are two industry standard methods required to mechanically test bond strength. One is bond shear test and the other is wire pull test. Both tests are destructive. That's why the tests are done during machine setup prior production run. The machine or process is not released to production until the test is complete with the pass result. Depending on the number of wires, the test is done on all wires or just sample of wires. The bond shear test methodology is a documented JEDEC standard JESD 22-B116 titled Wire Bond Shear Test. This is a pre-standard that you can download from JEDEC website. Wire pull test methodology is documented in MIL Standard 883 Method 2011 titled Bond Strength Destructive Bond Pull Test. If you have any questions, you can drop a comment or send me an email. Please don't forget to like, subscribe, and share this video. Thank you for watching.